Hello. We will wait for a couple minutes. Yes, we will start, I guess, like 5:35. All right. All right. Welcome everyone to my first workshop at AIS. So this workshop today is the emotion recognition in comics. Um, so what we, yeah. Well, by the way, I'm Eric. No, I'm a tech coordinator at AIS. So before we go into the workshop, I need to um, I need to guide you through to upload the Collab notebook from the GitHub. So first of all, you need to go to Google Colab and click to GitHub. Um, well, first you need to click to File and then upload a notebook. And click to GitHub here. So the notebook will be stored in, okay. And then click to GitHub and upload notebook from the GitHub repo. Okay, so after you, so the link to GitHub repo is in the chat. So here you paste the GitHub, the link in this section here and looking for the repo ImageProc. And then you go to the branch workshop. And then you need to upload this notebook here, ImageProc_workshop. If you are done with that, please let me know. All right, one. Any question for this? Okay, great, so cool. Okay, so briefly, so in this notebook, you need to do, this workshop is organized as an interactive workshop one, so you need to code along with me. All right, so emotion recognitions in comics is, at this workshop, you will learn about how to use both computer vision and natural language processing to identify emotions in the comic scenes. Yeah, what we're doing. So in this, basically, so basically, emotion or emotion recognition in comics is a challenge that you have to develop a multimodal that use image and text to classify motions. So the task is that, so here is the image sample. You have Tintin is dark and some text, forward text here. And and then given the text and image, you have to classify emotions. And here you need to identify 8 emotions: anger, disgust. By just looking at the image sample, right, I can say that Tintin and his friends, they are happy. So before digging into the models, let's get the overview of the model here. So given that we have the two inputs, image and text, right? So the first step is that we need to extract features. So, okay, for the image, usually we use convolution networks or CNN to extract image features here. And then for text input, we usually using recurrent neural networks or RNN to extract the textual features. And the red and blue boxes here, they represent our visual and textual features. So, however, the output of this model. Okay, can you hear me now? Hello? Okay, I'm back now. Great. Okay, let's go back to the task. Okay, so here your input is image and text, and then you, given those two inputs, you have to identify 8 emotions in this comic scenes. So these are 8 emotions here. So obviously in this um, comic sense, right, as a human, you can easily say that Tintin and his friends are very happy, but then we wonder like how the computers can understand if Tintin and his friends are happy or not. And to do this, we will develop a multimodals. So before digging deeper into the details of the models, I give you the overview of the entire model here. So here I have two inputs, image and text. The very first step of this model is that we need to extract visual features from the image and the textual features from the text input here. For usually CNN or convolution neural networks, they are used to extract the visual features. For text input, RNN or recurrent neural networks, they are used to extract textual features. The output of CNN and RNN, they are the red and blue boxes here. So here you have visual and textual features. However, the output of these models is it has only one output that includes 8 probability numbers. Basically, what you try to do is that you try to predict 8 probability numbers for 8 emotions, right? Again, you have only one output, but you have 2 features here. Because of that, between the feature extraction and prediction, we need a step called fusion here. Fusion is a step that you will combine both visual and textual features together. Um, okay, for the fusion method, how to do it, we'll discuss later on. So the roadmap for me to develop these models, or I call it the email record, is first is that I need to perform data processing, and then feature extraction, and finally I fuse visual and textual features together. Also, please let me know if you have any questions in the chat. All right, so three steps. So before, okay, yep. So in the so when we get into data pre-processing, what we need to do is that we need to investigate the data sample. So here, there's one of the data sample given by the organizer. So here, what you have here is that you have the facial expression of the character, right? And then you have the visual appearance. So most of the time, the facial expression does matter a lot in terms of identifying the emotions, um, right? However, in some cases, the text does matter a lot, such as here, such as the onomatopoeia. Um, so this text here, sometimes most of the time, they are used to express the fearness or the happiness, and the text purpose here, they also play important in identifying the emotion as well. Okay, okay. Now we go to image processing. So here I have two images, right? Yes. Um, the first thing we need to do is that we need to resizing our images together into a fixed size. So here I want I said that the fixed size 224 by 224. Well, to be honest, that a deep learning models, they can process or accept image of in any size. However, usually a deep learning models, they work with a batch of samples, and when we work with a batch of samples, they require um, you know, all the images must be in the fixed size or the same size, and that's why here these two images in a different size, they all be resized into um, the size of 224 by 224. So resizing is a very basic step in image processing. Another thing that I do is the image standardization. This step does mean that you convert any colors range into a family color range. In the sake of to make it simple, you can think that let's say you are given the this dark image, right? It's dark and it doesn't look unfamiliar. I mean, because the image is so dark, so it looks unfamiliar. In order to make it more familiar, we will apply the image standardization in order to convert from a dark image to a product image here. So it's easier to see and identify, like, okay, this is the image of the sea. So resizing and image standardization are two basic steps in image processing. Okay, for resizing, do parts get cropped out or it all gets squeezed, distorted fit? Okay, so in the image, in the resizing, actually I perform cropping and paddings. That means that, let's say in this image, right, when the image is larger than this size, I will crop it into the center. That means the top part here, upward, and the bottom part here, downward, that will be cropped. So the image that larger than the 224 by 224, that will be cropped into the centers. However, for an image like this, on the left side, if this image here is smaller than this size, then I will pad the black pixels. For example, I can pad the black pixels at the top here or at the bottom parts here. So does it answer the question, Rashmi? And also, I don't do the squish or distorting here. Yes. When you crop the images, probably that you're gonna lose like information. However, however, I would say it doesn't lose a lot because most of text purpose they are at the top, right? And usually the phase they are at the center of the comic sense rather than at the very bottom one. So cropping, it may lose some information, but actually when I do this project, I did some data visualization and I checked some images. I saw that the face of the characters, they are placed in the center of the image. So when you're resizing, you can change the you may not use cropping or padding. You can use resizing by squeezing the images into the the size that you want. And by that way, it will preserve all of the information. Okay, so good. All right. Now let's do the image processing in the Collab. All right. Let's switch to the. Hmm. Okay. Let's switch to Wait. Oh, sorry. This one. Okay. Now let's switch to the Collab notebook here. So here I have the notebook that has all the codes for you. So are you all in the notebook now? Please let me know. So the first thing you need to do is that you need to execute this block of codes. What does it do is that it will install all the codes necessary for you in this notebook, and here it also pre-train. I'm sorry, downloading the pre-trained models. So here, the pre-trained model is the model has some ideas of how to recognize emotions. So yeah. Okay. Um is anyone in the collab yet? Um, please let me know. Okay. So after we downloading the pre-trained models, next is we need to import some dependencies. So here we import GRE. So this is the package that used for regex pattern. CV2 is a pattern library for computer vision and image processing. Next is that we import TensorFlow. So TensorFlow is a very popular deep learning framework. We have used this to develop our own models. And finally, we use Matplotlib. So this Python package is used to visualize like data or print image into the notebook. Okay. Next is that here we import TensorFlow layers. So in TensorFlow, there are we will import functions to develop our multimodal model. Okay, so and finally here, we need to set the random seed to 2021. We need to do this because it guarantees that I would say your predictions, my predictions are stable. They are the same one. Okay, now, so here I have a sample. So when you look at this, right, you can see the guy here he looks like disgust, and there's a text right here. That's just the beginning. I have ever I have even bigger chops planned. Haha. Well, he looks like happy in some cases. All right. So after we investigate samples, you can see that the input that you receive is the comic sense or the image here, and the text right. Now we go to the image processing. Okay. So now what you need to focus on is this function ImageProc. So within this ImageProc function, um, you would need to you will do two tasks. The first one is to resize image by either cropping or padding. Another thing is that we will standardize image. So okay, so in order to resize image by either cropping or padding, we're gonna use this function here, right? Um, so basically here you just need to copy and paste it. Okay, so the arguments in this function is the input, which is your image, and then your height and the width. So the height and the width here is the expected height and width of the image that you want to resize. Okay, so do you know like, so probably very obvious, input here will be the image. So what's the height and width here? Does anyone know? I mean, if you know, just leave, leave comments in the chat. Which size parameters? Okay, give me a second. The size parameters. What is that? Yeah, right. That's the size parameters. So here, the expected size I save into the size variable here, which is a tuple. So the first element in that tuple is the height, and the second element is the width. So you just need here, you're gonna replace the height with the size 0 and the width with size -1 here, and there you go. No, so the size is tuple. So we're gonna use we're gonna index the height and width by indexing. Okay, does it make sense, Rashmi? Okay, so after we resize image, right? Next step is that we need to standardize. Oh yeah, that's fine. Um, you will learn it. Okay. Uh, well, size. Well, the reason is that here the tuple has only 2 elements, right? You can use say size 1, which is the second element. Also, because in Python, -1 it points to the last element, which is the second element in the tuple. That's why I use size -1. We can do size 1 as well, no problem. All right. Yeah, that's a thing that I love about Python. Um, all right. So when we standardize image, right, we can easily use this function. So this function will standardize our image quickly, and the input here, you just need to replace it with the image. So given the raw image here, right, the ImageProc function will resize image by either cropping or padding, following the expected size right here, and then it will standardize image. Okay, now let's build a function. Okay, something wrong. Okay, probably there's some indent things. Indent doesn't match any or indent things. Huh, what's wrong with this? Give me a sec. Okay, there's something wrong here. Um, yeah, good idea. Okay, FX. Thanks, Joe. All right, so here you just literally build your ImageProc function. Okay, the next things we need to do is that we need to configure the models with the image shape. So basically, we will save the expected image shape into the dictionary model configs. So in Python, model configs is a dictionary in all the languages is called the hash map. Yep. So here, the expected image size is 224 by 224. And the last number is 3. It represents for 3 color channels, red, green, blue, the very 3 basic colors in any image. Okay, good question. I think we can just copy the code line by line. Sorry for this. Okay. Yeah, just make a new cell. You can make a new cell by clicking the button code here, and then copying the code line by line. When you go to a new cell, you can easily just skip the comments, just copy and paste um, the code, right? Okay. 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 Does it work now? Correct me. Okay. Cool. So the next step is that we need to save the expected image shape to 24 and 3 to the model configs. So this one will help us to save, like, you don't need to like just repeat coding all the time. So here, let's execute the let's process the image sample here. So initially, your image has a shape of 493 by 225, right? And then we resize to 224 by 224. As you expected that some of the information they will be be lost. Um, Here the color they may change because of the image standardization. Okay. Okay, so this is before and after. Okay, now after we finish with the text processing, we're gonna move to the image processing here. Sorry, the text processing. My bad. So in the text processing, uh, so in this image, right, you have the text bubbles, you have the onomatopoeia, right? So we can extract it, all our text, and put into um, and here is the extracted text here. Okay, then most of the time the very first step in text processing is that we will lowercase our text, and this the result here. And then the next step is that we will replace all of the punctuation marks. So here I have 1, 2, 3, and 4 exclamation points, right? I will replace all of them with a special character I call punc with a square bracket at two ends. Um, Also, commas, periods, semicolon, colon, all of them will be replaced by the special character. The reason is that most usually the exclamation point they are used to express emotions. However, I did saw that in some text bubbles they have comma, period, and colon as well, and those punctuations they do not contribute to the emotion expression. And here's, there's some gap between exclamation points in all the punctuations, and because of that, I try to treat all those punctuation marks equally. So I replace all of the punctuation marks by the special character punc here. Make sure that the deep learning model doesn't focus completely on the exclamation points. They also consider all the punctuation marks as well. Okay, then the next step is that we will tokenize the text. Tokenize is a process that we split the tokens split the text into tokens or single words. And this is the result here. Another thing is I do is that I need to pad the text to fixed length of n. This step here is very similar to image processing, exactly as image resizing. So for every sentence that is shorter than, let's say I set the length n to 128 tokens, right? Then if any sentence that is shorter than 128 tokens, I will pad that sentence with a series of pad characters. So the pad here is you got a word pad with a square brackets at two ends, and for every sentence that is longer than the 128 tokens, they will be chopped off. Again, when we chopping off the text, we will lose some information. But yeah. But to be honest, that when I was inspecting the data, like the text, I saw that most of the text in this data set, the sentence, they don't go over 128 tokens, so it should be fine. Some of them they go over, they larger than 128 tokens, but just a very small numbers, so it doesn't matter a lot. Okay. Another thing is that the computers, they don't understand text, so they only understand numbers, so we need to convert from text to numbers. One of the method I introduced here is word embeddings. What it does means that, so here we will use, okay, I decide the length of the input sentence by actually I inspecting the distribution of the length of a text. So that inspecting text length is done like, it's done in advance. I just said, and then, yeah. And I saw that like averagely, the length of a text is around 128 tokens. So I picked 128 tokens as the length in here. Yeah, if you visit the repo, there's another notebook. It's called EDA note. It's the EDA. So in that notebook, there also the data visualization for as well. Oh, the recognize text and image. So that process is done by Google OCR, a service. Cool. So word embeddings is basically is a process that we will use a vectors or the array of float numbers to represent the meanings and the properties of the words. For example, here you got the cat and kitten, right? We cat, kitten, dog, and houses. We will use the array of 7 numbers to represent the meanings, and each float number here they represent like a small property of the word, such as living being, gender, or plural. Let's just look at those 3 properties. So cat and kittens, they are living beings, so their number is very high. Similarly for feline, but they are not humans. Because of that, then the value of human property of cat and kitten, they're very small. Now, when we look at the houses, right, you can see that because houses, it has the s at the end, so it's plural. So the plural property, the number at the plural column is high. Why we use the word embeddings? Because by using word embeddings, we can know like which word is similar to the other ones. For example, cat and kitten here, when we convert the array here into like XY plane, we easily compare distance between 2 words, and here we can easily see that cat and kitten, they are very close because they are animals and they look very similar to each other. However, for houses, they are not living beings and they're plural, so their distance is far away from the cat and kittens. And by using vectors or the array here to represent the meaning of the words, the computers can understand the text here. So the length of the word embeddings or the vector is defined by us. So the length here, I set it to 100. The number here, you can change to 150, but how I define the length end here actually is a trial error. Initially I tried 50 and then I increased to 100. So when you during the process of trial and error, I just try to find, I would select the best size of word embeddings for the model. Okay, now let's go to the Collab. So in text processing here. Okay, so to perform a text processing, I have a series of functions to do it. Okay, so the lookup function here, basically, it will help us build a dictionary of word embeddings to hand. So this this lookup function will help us to convert from a text to word embeddings. Okay, next is that now we need to look at the text proc function. And within this text proc function, you have a series of steps to perform text processing. So here you need to, the very first step is that we need to lowercase the text, right? So here we use the function tf.strings.lower. Okay, I think, okay, the input of a text proc is the text, the raw text, and the maximum length. Okay, here, so the argument for this function is text, right? So after we lowercase, we need to replace all of the punctuation and short forms. Okay, punctuations, as I mentioned, comma, period, exclamation points, short forms are what? Short forms you can are such as like in the negation, right? Usually, in some text they write as n single quote t, and all we know that is equivalent to not, right? Some other short forms such as like single quote m, they are equivalent to n, right? So we need to replace, I would say replace the short forms with is stems. So the regex replace will handle it. So this is function that I made it, so we will look at that later on. The next step is that we need to remove a trivial white space there. We do it because if there are multiple white space, then when we tokenize, then the algorithm may treat the white space as a word. Then it's gonna, I would say it's gonna make, I would say it's gonna make the deep learning model feel like it will trick the deep learning models a little bit. So I need to remove the trivial white space here. So to do it, I use function regex replace. So this function is from TensorFlow. This function is the one I created, so just don't misunderstand them. Okay, so the input to this one is the text and the patterns. The patterns is the regex pattern that we the regex pattern to recognize multiple white spaces. Okay, so to fill that one, here we will have the slash and slash s blocks. So this will guarantee that if we have two more white spaces, then we will replace two more white spaces with a single white space only. Okay. All right. So after we move the trivial white space, right, we need to I would say choice strings together. This step is necessary because, well, when we use Google OCR, right, Google OCR we will in this image Google OCR will return two text. The first one is from the text verbers, another one is from the onomatopoeia. So this sentence and this sentence, they are two separate texts. In order, however, because these two sentences they belong to one image, in case that we need to concatenate them together. And to do it, basically I use a function reduce joy, and to concatenate them I actually using a special character called sep. So this special character is used to notify that is the a mark starting how I say this set character is used to notify the end of a sentence and the start of a new sentence. Now we got the text here, and then we adding the separators. Okay. So after we join strings right, we need to tokenize it. So to tokenize, we can easily use functions split. Yep, that's it. And finally, we do paddings. Remember that. So for every text length, or every text that is larger, its length is larger than the expected length, we will chop off the text. Otherwise, we will pad the special character to the text to fill up to 128 tokens. So in order to perform the conditions here, we in TensorFlow they're using a function called tf.count. You can look at documentation of this function, but for quick, within this few lines, the thing you need to focus most is this function part text. So this function part text, it will pad the special character part to the text that is shorter than 128 tokens. So now and after you padding right, you just return the process text. Okay. Am I too fast? Okay, so now let's look at the part text function here. So in order to so the first step I did here is that I will store the special character path into the variable path here, and also store the text length into the variable text length right here. And then your job is to use the function tf.repeat here to create multiple copies of the special characters. So the number of copies should be equal to, should be the difference between the max length and the length of a text. Okay, so to do it, you're gonna use target tf.repeat, and then okay, let me see. All right. Okay, where am I? Oh, there we are. So you have the path characters, which is stored already in the path, this variable path. So I type path here, and the numbers, the repeats, is gonna be the basically difference between max length, which is the argument of this function, and minus the text length. Okay, and after you execute this function right, you will have multiple copies of I would say a series of path characters and store into paddings, right? And in order to do the paddings, actually, you need to concatenate the original text with the paddings here. To do it, you use the concat function here. Okay. All right. So up to now, we just finished the path text function. Now let's move on with the regex replace. So in the regex in this function, the input is a text, and our job is to replace all of the negation short forms with the not, and then replace all of the short forms of like is. This one can be represented for is or was, right? And this one could be were or are. So here we will replace all of these short forms with the verb be. And finally, here we will replace all of the punctuations with the special character punct right here. All right, for inputs, first step, replace the negation short forms. Okay. With that, you need to use this function. Okay, let me copy and paste here. So the input here will be the input here will be the word input here. Okay. Okay, next is the regex patterns. You're gonna replace the regex patterns with party, and here we aim to replace this short form, right? So we type and single quote T here, and your replacement. Oh no, you shouldn't use the single quote here. You should use double quote, just to like make it different from the single quote in the short forms. And your replacement, okay, gonna be not. So here I add a special, I add another space in front of not um, because let's say if I got the word doesn't, right? If we don't add the space in front of not, then we will have does not. And this is a word. There's not two single words that we want, so that's why we need the space in front of not here. Okay, now for this step, again, we use regex replace. We add, we put here inputs, and your pattern gonna be any string that matches single quote S, single quote RE, and single quote M, and you replace them with the word B. And here you still have the a white space for the B as well. All right. Finally here, you need to replace all of the punctuation marks with the special characters punc. Inputs. Actually, let me copy and paste it. It's easier for you. Yep. So here, any special characters. So here, what it says that for any characters that doesn't is not the alphabet, they will be replaced by the punch character here. Okay. And indent, where is it? Very careful. Okay. There's an indent error again. Maybe some indentation error here. Okay, I can fix it quickly here. Okay, I think probably that the indentation errors could be somewhere. I don't know, to be honest. Anyway, to make it quick, let's continue. Well, later on, you still have the access to the notebook with all the codes, but here, let's look, just follow my notebook here. Okay, so right after executing this block of code, right, you have TextProc that help you to process all our text right here. So if you still have the indentation errors, you can either like copy and paste code line by line. Otherwise, I would say you can you don't need to code. You just follow the notebook here. Okay. Okay. So after we build the TextProc function, we need to configure the text length here. So here I set 128. Okay. So now let's see what's the output of the TextProc function. So this is the original text, right? And after we process the text, we will have this. Okay, so first the original text that will come into the text box function, and this is the output. So all of the tokens or singles, they are separated. Special punctuation marks that are replaced by this special character, right? And then because the sentence is shorter than 128 tokens, then you have tons of padding characters here. The next thing is that here, after you got the tokens right, you're gonna perform the code tokens. So this process is that it will convert your tokens into a numbers. So 8827, it represents for the index of the word that in the word embeddings. What this means that so here we will maintain a dictionary of word embeddings, and we need to, so for every single token here, right, we will convert that word that into word embeddings through this index number. So that's why we, after we got the tokens, we need to decode tokens into the index numbers to retrieve the word embeddings. The word embeddings I will introduce later on of a notebook. Yeah, sure. I can send it. Oh, you got it. Okay, cool. Okay, that is the text processing. Okay, now after we process data, right, we need to extract features. So here, to extract the visual features, we use CNN or convolutional neural networks. Basically, convolutional neural networks, it mimics our human eyes. So initially, our eyes focus on, let's say, you have a fan in front of you and you try to recognize the fan, right? So what your eyes do is that they will initially focus on a tiny area of the face, and then scan the face from the left to right, from the top to bottom, and then it will zoom out to get a bigger view of the face. And again, it will scan through, and now your eyes will focus on the bigger area to capture the curve. The bigger curve here. So the scanning process repeated from left to right and top to bottoms, and then the idea is that CNN or our eyes try to get to capture higher level features by zooming out and scanning through the face, scanning the face from the left to right and top to bottoms. And as you can see that here, initially in a low level feature, right, you cannot see a lot of curve, but then in a medium level feature, you can see like the nose here, I guess, the eyes here, maybe the mouth and the nose right here, and then in the high level feature, you can see clearly the face. Okay, so to see clearly how it works, so here this square here with bunch of cells, right? This is your raw image, and and then CNN we will apply like it will focus on 9 cells right here and select the best cell and save it right here. And this process is will be repeated from from left to right and top to bottoms, as you can see in the GIF. So CNN try to focus on an area and try to get the best pixels from that area. Okay. Oh. Okay. So to build the CNN model, here I use a function called vision. So the input of vision function is image shape, which is a tuple of width, height, and channel. The channel here is 3, the number of color channels. Okay, so okay here. So the CNN architecture I use is StretNS50. The reason why I use it basically is based on trial error. You can use Resizing 150 or StretNS 152 or 101, but here I specifically use 50. Okay, so before so this architecture receive the inputs from us. So before we feed the input to the ResNet, we need to define the input layers. The input layer here, it requires a shape. So the shape here, you just need to pass the argument image shape. Okay, and then the output of this vision function is the poly of the resolution 50 that accepts any image of the shape 224 by 224 by 3 and outputs the its output is the resolution 50. Okay, oh, there we are. Image shape is not defined. Give me a sec. Where is it? It should be here for us. Oh. Oh. Where is it now? Oh, okay. This image ing, not the full text. Okay. Okay, so as you can see here, the input layers. So resolution 50, it will accept any image of the shape 224 by 224 and 3 color channels, and the output of resolution 50 is 7 by 7 by 2048. So here you can see that the original image of the size 224, right? There will be resized to 7. So this process, you can think of it as like you try to zoom in out, right? When you zoom in out, then probably that the size of image becomes smaller. So when the image becomes smaller, you need to increase. You need to so when you zoom in out, probably you can capture like higher level features, more curves, but then you may lose some very details. In order to save the details, here from the color channel 3, the ResNet increased it to 2048 in order to capture more features. And that's the reason why from initially you got 3 and then you'll end up with 2048. All right, now after we're done with the extracting visual features, so this model is used to extract the visual features for us. Okay, so after so after we extract visual features, we need to extract the texture feature as well. So as again, well, in some comic sense, right? Let's say this one, Spider-Man. Usually in emotion recognition, CNN is heavily used to extract like facial expression. However, like for this guy, for Spider-Man, his face is covered, so it's almost impossible to extract the facial expression here. That's why we need to rely on the text. And yeah, okay, and also in some other okay, there are other like edge cases, such as like in this comic sense, they have no proper text. So when we don't have proper text, simply we gonna fit like the empty string and adding the padding characters. Okay, so given the text, in order to extract the texture features, usually we use recurrent neural networks. Well, in this workshop, I specifically using bidirectional LSTM. So for the sake of to make it simple, you can think that RNN or LSTM is a series of neurons, and neurons is like it acts as memory in computers that it will learn that a neuron will learn a word at a time, and also it learns the relationship between the current word and the past and the previous words. So, for example, in the first neuron, right, it learns the word what, and then in the second neuron it learns the word time. But then you can see the color here is now the color is split into half, this one means that now this second neuron, it learns the relationship between the word term and what. And when you move from the left to right, which is right, so when we move and when the neurons like read the text from the left to the right, it learn the words and the relationship between the current words and the previous words. And the reason why the R and N goes from left to right because it mimics how we read the text. So here, why we introduce the bidirectional, because sometimes our text, well, actually by experiment, if we read from the left to right, then right to left, it will improve the performance of the models. In reality, actually, English is a language that we read from the left to right, but Hebrew, it is the language that is read from right to left. And hence here I use bidirectional RSTM to read the text from left to right and then right to left. Okay, for which ResNet to use, I would say it's a trial errors. You can try trial 150, trial you can try, I mean, either like VG16s, but it's like a process of trial and error. You the only way I can think of is like you need to test which one is the best for you and you use it. The reason why I use Resizing 50 because Resizing 50 is more architecture. So in this workshop, all the codes can run fast. You can use Resizing 152, but then it's a bigger models, bigger architecture. It just takes time for you to do it. Does it answer your question, Joe? One fun thing is actually Resizing 50 or VGG, they are very old models. Like they were brought back to like 2015, but they're still used until now. Alright, great. All right. Well, to be honest, I think this slide does answer a lot of things for you. Great. So okay. So here I have the input right. I got the word I stacker. I stacker the hook right. So each neuron it will learn the word right. So the first neuron it learns the word I. Then in the second neuron it accepts the word stacker and learns the stacker itself and the relationship between stacker and the word I, and so on. Okay, that's how the recurrent neural networks work. Oh, sorry. I'm sorry. All right, now let's go to the Collab and build the models. Um, okay, so here I have embedding layer function. Remember I mentioned about word embedding, right? So word embeddings will be handled by this function. Um, okay, so you don't need to type or do anything with this function. However, the thing I want to emphasize that in this embedding layer function, you need to receive so it requires the input dimension. This input dimension basically is I'm sorry, no, it requires the embedding dimensions. So this is the number that you identify. So in the past, I said that I set the embedding dimension or the size of the vector to represent the word meanings is 100. So so embedding dimension should be 100 here. What else? Yeah. Also, the embedding layers also require the vocab size. So vocab size is like how many like unique words you have in the text. So in some actually, if you bring this model into the production, right, probably that this model will see like the words that are not already in the vocabulary. In that case, um, the I would say in that case the model will not ignore, but like I would say they will ignore it for the sake of simplicity. Okay. So the embedding layer function will handle the word embedding for you. Okay, I will tell you where we use a function later on. Now let's focus on how to build the bidirectional AIS stream. So in this function, you can in this function it asks you two things: the forward units and backward units. So as said here, well, okay, where is it? So because in bidirectional AIS stream, right, it will go from left to right and right to left. So for the left row, which is the forward direction, you need the forward units, and you will use backward units for the backward direction. Okay, now let's build the forward direction here. So here you will use this function LSTM. Okay, the units here, you can replace the word units with forward units. Okay, for the return sequence, just keep it as it is. Okay, here I create the LSTM layer for the forward directions, so it goes from left to right, and by default, and because of that, you need to for this argument, you should set it to false. Okay. Now for the backward directions, you do it. You need to set it to true. And instead of forward units, you need to put into backward units. Okay. So after you got the forward LSM layers, you get the backward LSM layer. Now you need to so here all those two layers will be concatenated using this function bidirectionals. Okay, and thus you're done with building the bidirectional LSTM layers. Okay, so now we have a function to build bidirectional LSTM layer, a function to to build the embedding layers, to handle the word embeddings for us. Now, we will use those two functions to build your text models. So first of all, you need to define the input layer here. The input layer requires the shape of what? Okay, the shape here, because this is a text model, right? The shape of the input should be the max length. Let me see. Right. Yes, there should be text length. Text length is the maximum length of a text that you expected. Okay, so after you define the input layer, right, now the output of the input layer will be fed to the embedding layers. So the entire process done in this layer is that the input queue, there will be the raw tokens, the process tokens, right? So the process tokens, and then the process tokens that will go through, then the embedding layers will receive the process tokens as input and generate the word embeddings for you. So all the process is done automatically. So the output of the embedding layers will be like vectors of word embeddings, and then the embeddings will be fed to bidirectional LSTM layers. And here you need to build that layer as well. So here you need to use the biLSTM function that you define above. So for the forward units, so here, okay, I will set it to 256, and backward units set it to 256, and then at the end you need to have the embeddings here. Okay, now you might wonder why I choose 256, right? Again, it's a trial error. I usually, well, most of the time, you just try if the numbers, one like 256 doesn't work for you, increase it or decrease it. Also, here these numbers, they're equal because they are bidirectional LSTM. This means that when you use bidirectional LSTM, most of the time you should set two the forward layers and backward layers have the same number of parameters. Okay, still you can have a bigger numbers, no problem. But in that case, to be honest, I never tried it. But it's a good idea. Why not? Okay, so the output of the text function will give you the text model. Okay, so after you build the text function, right, you need to. So here I just basically just adding some parameters for the model, such as vocabs. So the vocabs here basically is a dictionary of the unique words in a text. However, I said none because I give you the pre-trained model, so you don't need to like upload the dictionary of words here. The vocab size I set to 10,000. The embedding measure I set to 100. Again, this number can be changed. Is trial and error. Um, the pre-trained embedding is none as well because you would use pre-trained models. Okay, so here you gonna use text function and basically just parsing all these parameters into the arguments of this function, and this is what you got. Okay, text length. Okay, give me a sec somewhere. Text length. It should be 128. Okay, return sequence is not defined. Oh yeah, okay, typo. All right. So input any text has the length of 128. Oh, thanks, Rashmi. And here your embedding layers will generate row embeddings. So here basically the output embedding layer is 128 vectors of size 100. So each vector it represents for a word. So here the embedding layers will generate 128 vectors of size 100 to represent the meanings of the entire string or text here. And embeddings will be fed to bidirectional arrestor, and the output of this is 128 and 512. 512 is what? Why you get 512 here? Because here, oh, where is it? So you have forward Unix 256, right? And the backward Unix is 256. And because we concatenate them together, so the sum up will be 512. That's why. Okay, great. Okay, so now you have a text model to extract text features for you. Oh no. Okay. Any question? Uh, okay, if not, then let's go to the last thing. Okay, now let's go back to, now we have, again, the overview of the architecture of the model that we developed. So here, red box represent for visual features, blue box represent for texture features, right? And we have only one output here. So because of that, we need, for the step fusion, we need to somehow like combine them together. So in order to do it, what is very simple method is that you just concatenate visual and textual features together. So these two small features will be concatenated and become a bigger features. Okay, so this big box here that we fed to the last section prediction here. So this section here, they are just series of fully connected layers. Okay, I will explain the fully connected layers later on, but just remember that our output that we want is a single output of 8 probability numbers. Okay, so those 8 probability numbers, they represent for how likely the emotion exists in the in a comic sense. Here, we try to identify all of emotion existing in a comic sense. Okay, next is about fully connected layers. The a neural net for fully connected layers is neural networks in the machine. If you took machine learning course already, you probably get familiar with neural networks. Why call fully connected layers? Because let's say from input right here, right, the input will be fed to this. It's called fully connected layers because for every neuron in this layer, right? Let's say this layer, then this layer, each neuron it accepts all inputs because, and then in the second neuron it does the same thing, accepts all inputs, and that process is done for all neurons in the layers, and because of that, it's called fully connected layers. So the series of stacked fully connected layers, they become the neural networks, and the neural networks here, it acts as the classifier for us that generates 8 probability numbers for 8 emotions. Oh yeah, sure. So okay, let's go to the output of CNN and output of RNN. So the output of RNN will be this 128 and 512. None here is just the number of samples in the batch. Yeah, it should be quick. The shape of the CNN is 772048. Yeah, it should be really quick now. Okay, is it clear, Joe? All right, so now we're gonna fuse those two visual and textual features together now. Okay, to make it very fast to wrap it up, let's copy and paste here. I know it's bad, but actually I think we are out of time. Just try it. Okay, so sure, Joe. So first, in this create model, right, we need to build in this create models within that function. We need to build the visual model to extract the visual features. So I just use a vision feature function that I define above, and similarly for text models, I use the text function to build the text model, right? And now, um, okay, one thing that wait, um, give me a sec. Okay, so I have vision model, text models, right? Here, the output of vision model and text models are these one. As you can see here, that if because the output share of these models, they are different, so it's impossible for us to concatenate them. So in order to concatenate them, here I will apply another convolutional neural networks here to convert the 2048 to 512, right? And the output of this line here will be 7 by 7 by 512. So now the last number of the CNN output matches with the output of the text model here, except for the what. Okay, now next is that here still we have for text models it has two 128 and 512 two elements, but for CNN it has up to like 3 elements here. So now I will fold the output of CNN together. So the 7 and 7 here that will be added together to become 14. So the reshape function here will help us to fold the CNN output to 14 and 12. Right now, we can concatenate the texture and visual features together. Okay, so in order to concatenate them, I use a function called tf_concat. Okay, that when so here I what else? Okay, so here I concatenate those features by the last axis, by axis one. The axis one it corresponding to this number 512 here. So okay, so so here I have concatenated features, right? I fed it to the fully connected layers. So in TensorFlow they call dense layers. Okay, and for the last layers, um, uh, also one thing, um, here oh great, see you later, Rashmi. Okay, so here I need to do flatten. So flatten here is that we need to do this because here we have two elements, right? But what we want is only 8 numbers only. So we need to like fold it up to have only single output with of 8 probability numbers. So that's why we do the flatten here. So the output of flatten will be like none. Let's say like some number here, only one element right here. And for last layers, we need to use a fully connected layers, and the unix here will be the number of classes, or it is 8 in this case, because at the end what we try to do is to predict 8 probabilities to predict the likelihood of emotions existing in the comic sense. Okay, we run it. Okay, here I just pass the num class parameter to the models, and this is what we got. Okay, so the image input is this 224 by 224 by 3. The text input is any sentence of 128 tokens, and the output is any predictions of 8 numbers. Okay, again, as I mentioned that here you don't need to train the models. I give you a pre-trained models. So here I load the models using this function, and here because here are also freeze models. Freezing model does mean that, well, in prediction you want a stable predictions, so you need to freeze it in order to make sure that the next prediction is to make sure that like your your outcome is exactly as the outcome is exactly the outcome of the other guys do it. Okay, so I get load the models. I load it up from the pre-trained models. Uh, a text down. Okay, so here now we got to prediction, right? Basically this step here, what I do is just prepare processed image and tokens for us. Okay, quick. Okay, there we are. Okay, next is that here we're gonna make predictions. Okay, now finally let's print the output here. A text time. Anyway, so here I have the input, the text here, I got the image here, right? And there is the output that I already made it. So here looks like the guy. So my model said that this guy has kind of like he looks like got a feeling of angry, fear, and neutral. Looks like so, or some kind of disgust here. Um, Yep. So that's how. So that's the end of. So that's how you build the multimodal model for recognize emotions in Comic Sans using both image and text. Okay. Yep. And thank you for watching. If you have time, please fill out the form. I will drop the feedback form here in the chat. If you have time, please fill it. Thank you. So, for you have any questions, I can answer. All right. Thank you a lot. Yeah, if you have any questions, you can just go to Discord. Uh, well, just mention me in a general channel of on a AS Discord, and I can answer your question. You're welcome, Uma. Uma. I'm sorry if I mispronounced your name. Great. I hope this workshop is helpful for you. All right. If nothing, I will stop streaming. All right. Then have a great day. Have a good night. Bye, guys.